Günaydın. Good morning. I'd like to thank PAGEV for the invitation, and I'm glad that all of you are here. So I'll try to talk about polymer rheology in the morning, and then in the afternoon, I'll talk about polymer extrusion. Of course, I have a lot of material to present. There are many slides that you have in this book that you have right here. And all of you, you have a copy. And also, this morning, it was sent to every one of you an email to download a book of mine. Did you receive it, some of you already? Okay. So in the book I have a lot of details because in the slides, of course, we have a lot of material and we will go rather fast. And of course, I cannot cover all the material, but in the book, you'll be able to find the details. So without further ado, I will proceed with my lectures. And as I said, we are going to have two sections: polymer rheology in the morning, and in the afternoon I will talk about extruders, screws, and dies. And during my presentation, I will also include a lot of problems that I have solved over the years. In other words, we will do what we call troubleshooting. Polymer rheology, in this first part, I will start with some polymer basics, but really, there's a lot of material that I cannot cover in the very short time that I have. Then we'll move on to viscosity, elongation of viscosity, viscoelasticity, stress relaxation, the role of rheology in mixing. I'll talk about extrudate, swell, shark skin, and melt fracture. This is the first example. It's good that I have this book. Okay, what do we do now? Okay? We turn it off, right? You can drink the water, but how is this made? Okay? You can see I have a big picture over there. And this is a problem that I have solved. The problem is with these bridges. You see those little bridges over there? Now, this is an injection molding problem. The gate is somewhere around there. The polymer is injected over there. It flows through here, and then it has to flow through the bridges, these very tiny bridges. You can take a look. There are bottles in the back, right? And it must fill this bottom ring. And this is difficult. And I have a customer, I will not say the name, it's a very big, very well-known company, a European company actually. And they could not. They produced a very nice polymer, but they could not fill the bottom ring. Why? I'll try to explain it to you later. This is the second problem. That's from long time ago. It was for the trains, the Amtrak trains in the United States, traveling between New York and Boston, and also other parts of the United States. They produced windows from PMMA. The windows, the glass, had a little bit of waviness in the surface. It's very difficult to see. I remember they brought a sheet of this material, and it was very, very nice. However, they told me that during the night, the people in the train were getting a bit dizzy watching the lights outside. And they told me, like, they had drunk too much wine, they were just, the lights were dancing and they were getting dizzy. And I said, how do they feel? They said, well, like drunk. So it was a problem that we had to solve. I'll tell you how we solved it and why. What was the problem? How did it come about? Another problem, a different one, it's blown film. It was a customer not very far from where I live in Canada, and he had a problem with shark skin. Well, the surface of the extrude wasn't very clear. It had some roughness. Usually the roughness is attributed to the phenomenon that is known as shark skin, roughness on the surface. But it was not. I'll tell you how we were able to solve this problem. A different problem, this one in Europe. My customer from Canada sold some material to a European country. It was machinery, actually, to make corrugated plastic pipe. Diameter was about 1 meter in diameter. And this pipe was subjected to a flattening test. A flattening test, you compress it and it will break. And it could not pass the standards required. It has to be flattened up to about 30% or 40%, I think, and it was failing. The question was, why? I'll give you the example together with the other material. Well, that's why, in order to do this, you really have to have a lot of knowledge about polymers first. So, in my slides, I have information about the polymer basics. I will not cover it here, just to show you things that you must read on your own in order to be able to understand. Well, it's about molecular weight and molecular weight distribution. I have a couple of examples. You can easily see that. I will not say very much, but you will be able to learn more, because in the book that was sent to you by email today, there's a lot of information, there are explanations, with examples, with numbers, which you will be able to follow. I do advise everyone to read this section in my book on molecular weight distribution, and what we need. All right? Now, I will briefly mention the different averages. MN is the number average of the molecular weight. MW is the weight average of the molecular weight. Okay? So what we have here is the number of molecules, and this is the molecular weight. And the number average, Mn, right, has the smallest value over here. So the average, this average, we can do the same thing for the age in this class. All right? Everybody's age, we are, let us say, 70. Everybody's age, we add them up. And we divide by the number 70 that we are in this class right here. That's the number average. However, we can take the square of everybody's age squared, sum it up, and then divide it by this, let us say, by the sum of the ages. And then we get another average. However, some people, like me, I'm old, and so my age, when squared, will have a heavier weight, so that this is called the weight average, and the weight average will be shifted to that point. And then you can take a cube and so forth, and you have the other average of the molecular weight. So these higher averages, they tell you about the breadth of the molecular weight distribution. You see? And this is important because polymers, some polymers may have narrow molecular weight distribution, some may have broad molecular weight distribution, and of course, the rheological behavior will depend on the breadth of the molecular weight distribution. So this is very, very important that everybody should know. And I say, first example, narrow molecular weight distribution. It's not very shear thinning. The viscosity does not change very much with the molecular weight. If it's broad molecular weight distribution, we have a lot of shear thinning, so it's, they're different polymers. And if you're producing film, if you're producing pipe, if you're producing injection molded products, this molecular weight distribution will have a very, very important effect on the processability and the end use properties. Another thing about molecular weight distribution, or architecture, if you wish, is branching. Now, this is really a cartoon, that we have a backbone and then we have branches. And you do not need very many branches to have important rheological effects. Just few branches. Let us say one branch per 10,000 carbon atoms. One branch. It will have important rheological effects. It changes a lot. So something else to remember is branching, and we'll talk about it. Crystallinity, of course, is important. Molecular alignments, crystallization, density, mechanical testing, all those important, basic, important things. I will not go over it, but it's in the lecture notes and better explained in the book, which I urge you I recommend that you study it. Well, you should remember just one thing is density versus material property, density that is, and the properties, various properties such as stiffness would increase, hardness would increase. However, some other things like ESCR, environmental stress cracking resistance, it drops, right? In fact, I have a problem troubleshooting where a polymer, high density polyethylene was used, and it had more density and it had inferior environmental stress cracking resistance. I think I have a problem also with polycarbonate. I'll show it to you later on. But important properties that you must know and understand. Heat capacity, also of importance, heat of fusion, crystallization, and melt flow index. Now, melt flow index is a very, very simple rheological test. We have a certain weight pushing against the polymer, and it is forced through a very small die. Diameter about 2 millimeters, length 8 millimeters. And although this test is not very sophisticated, it is used extensively in all polymer resin data sheets. And I think I have one, next one. You can see here, this is from Total, and you can see here the melt index. The weight in the melt index is 216, and the melt index is 0.15. And then if you put a weight of 21.6, it is only 14. That is, we have 10 times more weight, 216, and we go to 21.6. So this is 10 times larger weight. However, the melt index from 0.15 becomes almost 100 times larger, which means you only put 10 times more weight, but you get 100 times more material, which means that the polymer is shear thinning. The more weight you put, the faster it goes, shear thinning property, which is very, very important. Now, the intrinsic viscosity, for some material, it's a way of measuring the molecular wave distribution indirect way through measuring a viscosity. And in some data sheets, that's what you see, because it is difficult to do the melt index test if the polymer tends to absorb a lot of moisture. That's why I explained here. Again, I will go very fast. For PVC, if you work with PVC, it is another test, which is the K value of the PVC, which is like the intrinsic viscosity. The molecular weight and melt index. The molecular weight and is inversely proportional to the average molecular weight. Obviously, the more material comes out, the less the molecular weight will be. Pretty obvious. And here is a classification of different melt index values and where those polymers are used. You can take a look at it yourselves. And thermal properties. And I have some books, recommended books on polymers in general. So with that, I completed the discussion of the polymer basics. I simply indicated the important things that you must learn in order to be better able to solve some of the rheological and extrusion problems. Viscosity is the most important polymer processing property. It represents resistance to flow. And I remember reading a paper and somebody said, polymers love shear, which means that the more you shear them, the more you force them to flow, the less resistance they represent. It's a very nice way of putting it. It's another way of saying polymers are shear thinning. And this property, of course, we represent with this very well-known curve that the viscosity of a Newtonian fluid is constant. However, the viscosity of the polymer, it drops with the rate of shearing. So very, very important property to measure and understand. And because this is done, because we have a polymer, which is a collection of long chain molecules, and upon application of stress, they tend to disentangle, they align in the direction of the flow, and consequently, the resistance that they represent is reduced. And of course, we have this famous equation, the power law equation, eta, the viscosity, is represented by this power law equation. And here are some typical viscosity data. Typical viscosity data, as you can see, the data are these points. If we put a power law, it does a good fit for the high rates of shearing, but not a good job for the region of low shear rates. So we should know that. And also, we should also understand with what sort of rates, what sort of shear rates do we have in various processes. In an extruder channel, inside an extruder, let us say an extruder that my friend Abdullah Demirci is designed at Microsan in Gebze Kocaeli. Well, the shear rate, I'm guessing, is going to be probably around 100, maybe 200 reciprocal seconds. If we have, I'm sure there are several people from emballage, from packaging applications, film production, and in the die lips, the shear rate will probably reach 1,000 or maybe 2,000 or so reciprocal seconds. Now, in injection molding, the cavity filling, perhaps this was injection molded. When this was made, I'm guessing that the shear rates were probably 10,000. Now, in wire coating, over 1 million, maybe 4 million. So it's important to know the shear rates, if it, and the different processes. And this has a very important implications, like how the product is produced and what sort of problems are likely to have. We have these two models, the Karo Yasuda and the cross model, that they do a very good fitting of the entire curve. The parallel does a good job only for the high shear rate region, whereas the Karo Yasuda model and the cross model are very good in fitting the entire region of measurements. And then there is dependence of temperature, dependence of viscosity on temperature, which is exponential and depends on the polymer that you have, how much influence the temperature will have by, let us say, increasing the temperature by 10 degrees. What is the difference on viscosity and so forth? Also pressure. Now pressure does have influence on viscosity, and we do not really use it in extrusion, but we do use the effect of pressure on viscosity in injection molding, because in injection molding we are likely to have very, very high pressures, perhaps 200 megapascals, that's 2,000 bar. It's a very high pressure. In extrusion, we can go perhaps up to 40, 50 megapascals, 500 bar or so. So in extrusion, we do not really use the dependence of viscosity on pressure in any calculations, but we do use it in injection molding. And how do we measure? Well, the two most common instruments are the capillary viscometer and cone and plate or parallel plate. And it's important, the capillary viscometer, the measurement is not that simple. If you want to have good measurements, you really have to perform some corrections. And in the book, that each one of you has a copy, I do explain in great detail how we perform these corrections, the Rabinovich and the Bagley correction, to get good measurements using a capillary viscometer. Otherwise, you're going to have errors 20 to 40%. So sometimes, okay, you can live with it. But sometimes you must have more accuracy. Rotational rheometers, they have a limitation, because if you rotate too fast, the material first has instability, and eventually it will fly out of the contraption that you have for the measurement, the rotational rheometer. So this one has limitations in the range, and I'll tell you later on about the oscillatory mode. So capillary viscometer measurements are used very frequently in extrusion. Depends how expensive the instrument is. uh, how good it is, usually may go from 5 to 2,000 reciprocal seconds, but it depends, like there might be even better than that, but it depends how much money, because one capillary instrument, a good one, will cost at least 100,000 euro, okay? Well, Göttfert in Germany will sell you a better one for 3,000 euro. If you can afford it, you can do more accurate measurements. We should remember that for flow in a tube like this, we have the velocity profile, which is, well, quasi-parabolic. The shear stress is linear, all right? Zero is at the center, maximum at the wall, all right? And the shear rate varies again from 0 to a maximum value at the wall. So when I say shear rate at the die lips of a die, I guess die is kalup in Turkish, right? Kalup. We talk about the value at the wall, right? Because right at the center, the shear rate is 0, maximum value at the wall. And now we come to another point, which is the so-called slip at the wall. Now, the fundamental, perhaps a cornerstone of fluid mechanics is that when you have flow in a channel, the velocity of the fluid at the wall is 0. That's a cornerstone of fluid mechanics. I've written a book, 815 pages, and everywhere the boundary condition is at the wall, the velocity is 0. Okay? However, yes, if I'm dealing with water, if I'm dealing with air, I can deal with oil in pipelines, this boundary condition is correct. With polymers, you know, polymers behave in very strange ways. Polymers nearly always exhibit some wall slip, and you have to measure it. When? And you will see a problem. So if I have wall slip, no wall slip, this is the velocity profile. If I have wall slip, you see we have this, a rather flat profile, and then you have slippage at the wall. Okay? So this is of very special importance, as you will see. To measure it, I will not go through the details. I have an example in the book where you see how it can be measured. So the wall slip can be measured using a capillary rheometer. And I tell you how to do it. And yes, we measured it. We measured it to solve this problem. Here's my bottle again. All right? Twist of cap. How did I solve the problem? I showed the first one, the first problem I showed this morning. The customer told me it was a very big resin producer. Everybody knows if I tell the name, but I will not. He said, there is one resin, I presume, a competitor, resin from a competitor, had no problems. They produced them without any problems like this. They gave the second resin, and the plant, no injection molding machine for producing those twist-off caps could function. All right? Both resins, resin A and resin B, had the same, about the same viscosity. They did provide me with viscosity curves and all that. They had measured molecular weight distribution, a lot of work, and they should. So the resins they thought were identical, A and B, they thought that they were identical. The problem was, as I told you, that the polymer must travel from here, the gate, through those tiny bridges to fill the bottom ring. But these are very tiny bridges. The diameter was 0.3 millimeters, which is probably what I see right here. It's about the same, about that. This one's even thinner, I think, less than 0.3 millimeters, this one. And it could not be filled. So what happened? We did some calculations of the shear rate. We did actually some very simple calculations, and then we followed it with a computer simulation of the flow through this tiny capillary of 0.3 millimeters, all right? And we found that the shear rate had to be over 100,000. And the shear stress at the wall, 0.9. Okay? That was my calculation. And I said, oh, since we have so very high shear stress and shear rate, we must have wall slip. So we started measuring it. All right? We measure wall slip of resin A, and we measure wall slip of resin B, and they were very different. And that was the problem. The customer, I told the customer, I said, listen, the competitor resin has higher wall slip. It flows easily through the bridges, whereas your resin does not. So the customer sent me another resin and another resin. It was, I think, number 14 or 15, I don't remember. He was doing something. He never told me. They never told me what they're doing. They never told me. And then, after receiving 13, 14, I don't remember, maybe 15, a sample, I said, yes, this is good. They went to the machines, they produced it in large quantities, everything well, the problem was solved. And before coming here, I checked the data sheets of this resin. I went to the website. I mean, The customer did not, the customer never told me what they were doing. Okay? But I knew the code number for the resin, and I punched on the internet, you know, resin producer, name, number of the product, and what do I see? Spelled out, black and white, this resin contains a slipping agent. So they added a slip agent in there. Okay, that was the problem. But you see, like, the customer, they had done everything else. They had not added this slip agent in. So now the problem was solved. But how we solved the problem? Because when I saw with my calculations and simulation that I have very high shear stress, very high shear rate, right? I must have wall slip. It was HDP, high density polyethylene, right? Problem was solved. So that's why we used rheology to identify the problem. My customer never told me what they were doing. They added slip agent, problem went away. And I see it on data sheets. Okay. The melt index. The melt index test is, of course, the most common device. It's not really a rheological device. It's rather a quality control device. You might say, well, it looks like a capillary rheometer. I would call it like a low-tech, low-technology capillary rheometer. But you can get, and whether we like it or not, it's there. You know, we cannot ignore it. Like in some very theoretical books on rheology, polymer rheology, you will never see a mention of melt index. But can I ignore it? You know, 400 million tons of plastics are produced per year, and 95% of them are sold on the basis of melt index, so I cannot ignore it. You see, like, it's interesting to notice the melt index, the standard weight is 2.16 kilograms. And I remember I was teaching at McMaster University, and one student said, "Professor, why is it 216? And, you know, we professors have quick answers. And I said, it's conversion from pounds, the British system. It's conversion. Well, it's no conversion. It was the original weight was 216, and you must understand the story, how it came about. I have corresponded with the inventor of this method, a fellow from working for ICI, Imperial Chemical Industries, in Britain in the early 50s. He was a young man at the time. Now he's over 90. He was alive 5 years ago. I corresponded with him. He was alive. And what happened was that his boss gave him the job to evaluate different resins. He had a weight of 1 kilogram. He had a weight of 5 kilograms, 10. 1, 5, 10. One was too light. 5 was too heavy. Well, he looked around, and they had, for the door, they had a door stopper, which was an old iron for ironing. How do you call it iron for? Okay? It was an old iron. He put it on, well, 216. and then he goes back to, he told me that he went back to his boss. He said, well, I have done it. Here are the measurements. Now I know how to do it better. His boss said, no, this is good enough. So we have it. So if we have it, we better know how to explain it. And it's actually a good test, actually. It's easy, quick, and so you really have, so in the book that you all have, I explain what are the problems with it, all right? You know, it's like a low-tech capillary. It has some inaccuracies. You will see there what it means. You can get one low load melt index. You can get a high load melt index. From the two, you can approximate almost a viscosity. It's not very accurate, but you can approximate. With melt index. Did I solve a problem with melt index only? Yes, I did. Well, that was in Canada. And this is an actual picture of those traffic lights. This is the housing made of polycarbonate. And they asked me to go there because they thought it was a problem with flow in the mold. That's what they thought, flow in the mold. And I started asking questions, and we did some experiments, and we realized, it's something that I knew from a long time, this was from an old book, and it is well known that the environmental stress cracking resistance, right, drops as the melt index increases. In other words, the resistance to cracking, okay, drops as the molecular weight becomes smaller, right? I knew that from a very old book. And then by making measurements and correlating to performance, we said that if the melt index was less than 12, they never had a problem. All right? Between 12 and 18, well, sometimes working, sometimes not. For more than 18, it was always bad. So what was the solution? Measure the melt index. Problem was solved. And in fact, it's a funny story. This was a processing company when Yusuf were talking about processing in general. They did not have in this company a melt indexer. They were receiving the resin. It was a fairly big company, 350 people working there. So they would receive the company actually from General Electric. Now it's Sabic. There are a couple of people from Sabic. Okay? It was, all time was General Electric. Now Sabic will not deliver that kind of product. Anyway, it was General Electric polycarbonate. At my customer's plant, they did not have a melt indexer. to measure the melt index. So they did not really know, and there were variations, like sometimes it was 10, sometimes 15, sometimes 20. And I told them, I said, listen, you should never injection mold anything having a melt index larger than 12. So what they would do, they receive the resin, put it in a bag, ship it back to General Electric by FedEx, measure the melt index, report back, okay? That was the solution. Because, you see, we talked with Yusuf about it, many of the resin processors do not have sophisticated, equipment or any equipment for that reason. So, a problem, a very serious problem, because they were cracking the housings of traffic lights, and we have very severe weather in Canada. I mean, temperatures drop to easily to minus 20, and where I live, in Toronto, the record temperature is minus 30, and of course, snow and rain and whatever, very difficult environment. So they had to withstand, and by having products with melt index less than 12, it was always working, so the problem was solved. Well, here I have some typical molecular weight distributions, long chain branching, sort of how they affect the viscosity, which you can check. And here is a combination of other things to know about it. Another problem is, which you should be aware, is viscous heat dissipation. That is frictional heating. Because the polymer has a very high viscosity, it generates, of course, heat. And this can be very, very large. Typically, in a tube, we see that we have viscous dissipation, which is going to be highest near the wall, because that's where we have the highest value of the shear stress. High shear stress, they go together. Eventually, if you go like this, it would sort of penetrate towards the center. Eventually, if it is a very long tube, it will get like this. Now, you can easily determine sort of what we say in North American English, ballpark. This expression means an average value by taking the pressure and dividing by the density is the pressure divided by the density and the heat capacity, and you get an approximate value. And you can see that this is the value can be, right here is 5, but in some cases, it can be very, very high. You can, and I do remember, because I sell also computational software, commercial versions of software. And I remember one customer, I said, I sold him software. I did not know whether he got anything out of it or just doing calculations. He told me, yes, I solved one problem. They did have this kind of profile, locally, very, very, very high temperature, and they did not know. And then they modified the problem, and they solved it because they knew what was happening. So you can have locally very, very high temperature. Can be not just 5 degrees, it can be 20, 30 degrees. And if you have a temperature sensitive material like PVC, you're going to have local degradation. Well, in fact, this is a computer simulation. And you see, this is a converging die, and you see how the temperature builds and gets very high value. It's 160 at the wall, we have 170 over there, and it can be higher than that, and something that you have to calculate. And the important thing is to be aware that viscous dissipation is very important. Here's a summary of what the stuff that I talked about is. Well, I talked about so far about shear viscosity. Shear is very easy to generate. I'm shaking this water bottle, I generate shear. Well, elongation is much more difficult, and it has very important implications. Now, we defined viscosity. Well, I should have said shear viscosity. Shear meaning like a deck of play cards, you shear. But at the same time, we can also define the resistance to stretching. Of course, it's difficult to imagine stretching of water, but polymers are very thick, and therefore we can measure resistance to stretching. And resistance to stretching is equivalent to resistance in shear. And what is the relation between the two? Well, the resistance to stretching, that is the elongational viscosity, is three times the value of shear. And this was discovered over 100 years ago, I think it was 1905 or so, by Troughton, a professor at Cambridge or Oxford, I don't remember. And this is for Newtonian fluids. And it can be easily shown, and I have an example in your book, how you can prove this very rigorously with very simple equations. Takes one page, that you say for Newtonian fluids, the ratio between elongational viscosity and shear viscosity is a factor of 3. But for polymers, under usual processing conditions, it will go perhaps up to 100. And for some solutions, may go to 1,000. I've seen measurements up to 15,000, the ratio for solutions. For molten polymers, perhaps up to about 100, the ratio. And measurement is rather complicated, and an instrument was developed in the last 15 or so years. This is called the Centmanat extensional rheometer. Centmanat is the name of the person, somebody that did his PhD with John Deely at McGill University. And he's got this contraption which can be attached to a rotational rheometer. More frequently, in industry, they talk about melt strength. This is more of an engineering measure. It's more of an engineering measure. And you have a contraption like this, you stretch a strand, an extruded of a polymer, by a pair of rotating rolls till it breaks. And the force required to break the strand is the melt strength. So it's like the melt index equivalent. Melt index for shear, melt strength for elongational. You can relate it that way. And so this is an important measure in some processes. If you are dealing with films, with fibers, also if you're dealing with pipe production and so forth. Like, it's important in thermoforming. I think the company of Mr. Eroğlu is in thermoforming business, right? Right. Well, in that case, elongation of viscosity or melt strength is very important. For example, if you have low melt strength, the cups or whatever they make at Mr. Eroğlu's company will rightly break. And that happens, or it might be difficult to thermoform and get a good shape if it's too high. So it is a very important property if you have a production method, a processing method involving stretching, involving extension, like in blown film, like in, of course, yes, in blow molding, in thermoforming, in foams, for example, also. Well, I have an example. That goes back to early 1970s. It was in Montreal, and we had a session on industrial rheology. They had 3 resins used in extrusion blow molding, making milk bottles from polyethylene. One resin gave excellent bottles. The second, well, maybe. The third, I remember we were 200, maybe 250 rheologists in that session. It was a beer session, you know, drinking beer and talking. And the question was, why, you know, resin A? Well, it was a case of melt strength. Probably we did not have measurement, you know. For resin A gave excellent bottles. That resin probably, because they had no measurements at that time, that resin probably had high melt strength. So the polymer is able to stretch to form the bottle without breaking. Whereas the resin C, weak melt strength, you blow it, it breaks up. So no product. Well, I had another problem now in pipe production. I got a call from a customer. I knew them. I had done some work for them. And they called me. They say, we have trouble producing polypropylene pipe, small diameter. And then I said, yeah, that's sometimes the case because polypropylene has low melt strength. Polypropylene as a polymer is known to have low melt strength. He said, yes, but there is another competitor. And they have no problems there. How come they have no problems and I have big problems? Well, I said, these guys that they have produced good pipe probably have branched polypropylene. Branched materials have high melt strength. That was a guess. I said, talk to the supplier of your resin, whoever it might be. Ask them to give you branched polypropylene. He did. He was happy. Okay, problem solved. It was just, and it was over the phone call. He did not even pay me. Okay. Well, this is a very interesting graph. I like this one. It was an infomercial that appeared in Modern Plastics way back, well, 20 years ago, as I see. And what they have here, they call melt tension, is really melt strength. And this is the conventional polypropylene. This is very low. Here is the melt index, and it's very low. They produced a new polypropylene. They produced a new polypropylene, which is called New Strand. This is a Japanese company. And they say that this is an advertisement, just or infomercial. Long chain branching in the polymer through special reactor conditions. Decrease melt strength sufficiently to allow production of large thermoformed and blow molded parts. So, branching for polypropylene in particular, because polypropylene has very low melt strength. So, if you're producing a pipe, right? The pipe collapses by its own weight, it has no melt strength. If you have branching, no problem. So this is another solution to a very practical problem. Okay, now we are going to have the cafe break for half an hour according to the program. I think the cafe is right here, I think. And we'll start. I'll give you half an hour, 5 minutes after 11, okay?
Molecular weight, chain and tangle
Yeah.
in 9